Hello, today we're going to talk about limiting reactant and percent yield. So basically what this is you have a collection of reactants, and in order to make products, you may not use all of them. So one of them might run out before you use all of them, and so the one that you would run out of would be your limiting reactant, and then whatever you would have left over would be excess reactants or reagents, as it says here, but we usually call them reactants in class. So, as an example, we did this a little bit with the s'mores as well, but we'll go back to the cheese sandwich example that I've been using. So if you have a cheese sandwich, or you're making cheese sandwiches, and you have 10 slices of bread and 3 slices of cheese, right? You can make 5 sandwiches from your 10 slices of bread, and you can make 3 sandwiches from your 3 slices of bread. So your limiting reactant here is going to be the cheese. That's going to run out before you get to 5 sandwiches, right? So our theoretical yield, the amount we should be able to make with the reactants we're given here, is 3 sandwiches, and our limiting reactant would be the cheese, okay? So now let's do an example with actual chemicals. So in your notes, I've given you the steps for solving these, all right? And I'm going to go through them, but you can refer back to these steps as we do more problems in class. All right, so the example I have here is carbon monoxide plus H2 gas makes CH3OH. All right, so if we have 3 moles of carbon monoxide and 5 moles of H2, how many moles of methanol, which is the CH3OH, can we make? All right, so we need to do this problem twice, once for 3 moles of CO and once for 5 moles of H2. All right, so now let's just give ourselves a little bit more space to do this. If we have our balanced equation, so the first thing we need to do is make sure our equation is balanced. In this case, that means we're going to need 2 moles of H2 in order to balance it. All right, so you can go back and double check my work if you want to. All right, so if we have 3 moles of carbon monoxide, all right, 1 mole of carbon monoxide will make 1 mole of methanol. All right, so it's just a 1-to-1 ratio, so we should be able to make 3 moles of methanol with that. All right. If we have 5 moles of hydrogen, we need 2 moles of hydrogen to make 1 mole of methanol. All right, so the amount of methanol we can make from the hydrogen we're given is 2.5 moles. All right, so we can't make 3 moles if we only have enough hydrogen gas to make 2.5. So that is going to be our theoretical yield. That's how much we can produce. All right, and our limiting reactant will be H2 because that is the thing that's going to limit how much product we can make. All right, here's another example. Let's say we have 5 grams, all right? So we in the last lesson, we did grams of one thing to grams of another. Remember, it's the same process we were just doing. We'll just have 3 conversion factors, right? So if you want to pause here and get your molar masses for carbon monoxide and hydrogen, you can go ahead and do that. All right, so just to walk through, 5 grams of carbon monoxide. That's the molar mass of carbon monoxide. We know the mole-mole ratio from our balanced equation is 1-to-1. All right, and then 32.042 is the molar mass of the methanol. All right, so if we have 5 grams of carbon monoxide, we can get 5.72 grams of methanol. All right, if we do the same thing for hydrogen gas, right, we can use the molar mass of H2. Remember, that's a 2-to-1 ratio. And then the molar mass of the methanol is the same. So we could get a whole lot more methanol from 5 grams of hydrogen than we can get from 5 grams of carbon monoxide. But we can only make the smaller of the 2, right? We will run out of carbon monoxide before we get to this much methanol. So that is our theoretical yield. And carbon monoxide in this case is our limiting reactant. All right, so you can see it makes a big difference if you're doing grams of something versus moles, because we had equal grams here, but carbon monoxide is a lot bigger, and so will, not give you as much product. All right, so the last thing I want to do is percent yield. So the example I have here is using s'mores, which we've done already in class, all right? So if you have enough supplies to make 50 s'mores, but you load up your stick with 5 marshmallows, and get distracted and they get melty and they slide off into the fire. All right, now we don't have enough marshmallows to make 50 s'mores. All right, but if we are careful with all the rest of them, we should be able to make 45 s'mores. Right, so our theoretical yield for this problem would be 50 s'mores. That's how much we should have been able to make with the ingredients we were given. Our actual yield here is 45 s'mores, all right? And in the lab, it's not usually like you spill reactant or something. It's that, you know, reactions aren't perfect. You don't always make everything you could, all right? And then our percent yield, we'll be able to calculate, slide myself up here, with the part over the whole. Remember, that's how we always get a percent. So in this case, it's the part we actually made, our actual yield, divided by our theoretical yield, times 100, okay, and that 45 divided by 50 times 100 would give us a 90% yield in this case. All right, so now let's do an example. Okay, we have lithium hydroxide combining with carbon dioxide to make lithium bicarbonate, right? So if we do the reaction and we use 50 grams of lithium hydroxide, all right, and then we actually get 72.8 grams, all right, then what is our percent yield? So the 72.8, the amount you actually get, would be your actual yield. You must be given that in the problem. You can't calculate the actual yield. You have to just measure it in the lab. But we can calculate the theoretical yield. So we're going to take our 50 grams of lithium hydroxide and figure out how much lithium bicarbonate should we have made, okay? So if we had 50 grams, this is the molar mass of lithium hydroxide. It is a 1-to-1 ratio because this is already balanced. You should always double check that your equation's balanced, but this one is. All right, and then this is the molar mass of the lithium bicarbonate. So in theory, we should have made 142 grams of lithium bicarbonate. All right, but we only made 72.8. So our percent yield is going to be our actual divided by our theoretical times 100. All right, and note, you should never make more than the reaction, than the theoretical yield, all right? Your percent yield should never be more than 100%. If it is, then you've violated the law of conservation of mass. Probably you have extra reactant in there that you're measuring or something, but it shouldn't be that way. I shouldn't give you a problem like that. So if you end up with a percent yield over 100, you either swapped the actual and the theoretical, or you have a mistake in your calculation for percent yield. All right, so that is how we do the calculation for percent yield. Actual, which always has to be given in your problem, divided by theoretical, which almost always I will have you calculate from the reactants, and then times 100.